The first clues about how neutron stars might be visible came from a very unexpected source. That is, from radio communications here on Earth at the beginning of the last century. You know, when you listen to an AM radio, sometimes you can pick up radio signals from thousands of kilometers away, and that's because those radio waves are bouncing off the ionosphere, the part of the atmosphere that is ionized.
Yeah, I mean, normally radio waves just go through air, they don't bounce. To make them bounce, you have to make it ionized, split the electrons off from the protons and the nuclei. But how are you going to do that for the atmosphere? I mean, the atmosphere, at least down here, is pretty neutral. But it became clear from about the 1920s onwards that there was a layer somewhere up high, it couldn't actually go up high enough to visit it back then, that was ionized. And the amount of ionization depended on what was happening on the sun, particularly the sunspots. When there were lots of sunspots, it was more ionized. So somehow, something from the sun was reaching out and making the upper layer of the Earth's atmosphere, stripping the electrons off. So how's that going to happen?
Yeah, and the sun, you know, is only 5,500 degrees Celsius. So you need to have something that's a lot more energetic than that. And so if we recall the electromagnetic spectrum we have, optical light here, infrared, microwaves, radio waves, and then the things that we need to ionize, like the nitrogen that's in our atmosphere, very energetic. We need X-rays or gamma rays.
Yes, a visible light photon won't ionize anything pretty much. It just goes through, light's transparent to that. Radio waves, microwaves, infrared don't do anything. We need things up at least ultraviolet and probably well into the X-rays, which have enough oomph in every photon to actually slam into a nitrogen or oxygen and knock the electron out.
Right.
But the trouble is, remember black body spectra we've talked about, to get X-rays we're going to need temperatures of millions of degrees. And the sun is 6,000 degrees, 5,700 or something like that. That's and emits invisible.
Yep.
So how can the sun produce something with enough energy to produce the ionosphere? But we know the ionosphere is there.
Well, maybe we just need to take a good look at the sun and not posit what the sun looks like to our eyes, but what it looks like at high energies.
Okay, so we wanted to actually see if X-rays are coming from the sun. The trouble is, if you look at different wavelengths here, we're plotting wavelengths at the bottom here, and here's how much of them get through the atmosphere. And you can see that at most wavelengths in the X-rays don't get through the atmosphere, which is kind of weird. Visible light gets through mostly when it's not cloudy. There are various particular infrared wavelengths that get through. We spend a lot of our lives observing in these different windows over here. And radio waves get through no trouble at all. But X-rays don't. This is kind of odd because you think X-rays penetrate. They can go through the human body. Superman has X-ray vision and can look at your guns in people's pockets and things like this. But in fact, it's the same trouble. X-rays, because they ionize stuff, they have so much energy, if you put them through a lot of anything, they will ionize it and get stopped. So the atmosphere above us is very, very thick. X-rays can get a few meters through the air, but they certainly can't get through tens of kilometers of air. So it's kind of curious that Superman's X-ray vision would be pretty useless. He wouldn't be able to see more than a couple of meters away. And there'd also be no light for him to see by. I mean, we see because you get sunlight coming down, bounces off Brian, and so I can then see him. But there are no X-rays coming through, so I'd have to have an X-ray torch. Maybe if Superman had an X-ray torch, you could shine X-rays, but then they wouldn't bounce back if I was trying to see what was in Brian's pockets. The X-rays,
Yes.
they just go straight through out the other side. So I need an accomplice to run around the far side and fire X-rays so I could see it. So I think X-ray vision is pretty useless, really.
But it does tell us, getting back onto the point here, that if we're going to go out and look at the sun, we're not going to do it from Earth. We're going to have to do it above Earth.
Which, until the 1940s, was impossible. But during the Second World War, some very clever Germans invented ways of getting things up into space. And so after the war, people were trying to figure out, could we use these new rockets the Germans had come up with to get a detector high enough to actually see if the X-rays are coming in? So the first thing they needed was a detector. And the idea is basically what's called a proportional counter, and is very similar to a Geiger counter. You get some gas in a container. You have a very thin window at the front, and you make the thickness of that window just right so it'll let X-rays through, but it won't let ultraviolet and visible light and so on through. And if an X-ray will get in here, and it will get into the gas, and it will ionize it. It will knock an electron out. And then you put a very strong negative voltage on this cathode in the middle here. And that will start, that means that the electron will start accelerating towards it, and accelerate really fast if you put enough voltage. As it moves closer and closer, it'll hit other atoms and ionize them, giving you more electrons, which in turn will go and hit more electrons and more electrons, until you get a huge pulse of electrons hits the wire.
You get a big cascade. So one electron then cascades into this whole flood of electrons.
Enough that you can detect, so you should pick up a big pulse of
Electricity, effectively, when
Yes.
you measure it.
And so you can count those X-ray photons. Then you need to get it into space. And so you generally use one of these things, a V2 rocket.
A good use of a V2.
Yes, my father, growing up in London during the Second World War, had a bad use of a V2. He was sitting in his lounge eating his breakfast when there was a huge explosion at the end of the street. One of these things had landed on the end of the street. His main memory of the fact was it blew in all the windows in his house and got ground glass into his sugar bowl. And sugar was rationed. And they couldn't eat that sugar. They had all that lovely sugar that looked perfect, and they couldn't eat it from then onwards until the next ration came through because it had glass all over it. It's funny what people remember about these things.
So we could go through and use something like this to look at the sun. So let's see what the sun looks like with a modern detector.
Okay, so here's a modern movie of the sun in X-rays.
Ooh, so you can see the sun is glowing in X-rays, but not the disk of the sun. It seems to more almost be like a fog of stuff above the sun that's glowing in X-rays.
And these lumps of X-ray stuff are generally over the sunspots. So somehow it seems that while the surface of the sun is much too cold, the surface of the sun is black at X-rays, we're getting it above, which is weird. Normally in a star you think it's hot in the middle, cold as you go further out. And that indeed is what happens in the sun generally. It's several million degrees in the middle going down to only 6,000 at the surface. Only 6,000 degrees. Only an astronomer could say that.
Yes.
But then when you get above the surface it gets hotter again, but only in spots near flares.
So that's a very complicated process that we're not going to talk too much about, but it involves magnetic fields and particle acceleration and all sorts of other processes for another course.
And there are people who spend their lives studying it.
Yeah. But it does, the sun is very nearby. It's only 150 million kilometers, but that's 100,000 times closer, or even more so, than the next nearest star, and we can barely see the sun in X-rays. So it seems like the end of X-ray astronomy as we know it.
Yes, that's what a lot of people thought. X-ray astronomy was just going to be the study of the sun. And that was interesting because ionosphere, and that's important for military communications and things, which is why a lot of the people were funded to do this. But was that going to be the end of X-ray astronomy? Was there anything else they could see? I mean, the sun is, about 10 to the 11 metres away. The nearest other star is 10 to the 16 metres away. So that's 10 to the 5 times further away. Flux goes as 1 over distance squared. So that means anything else like the sun is going to be 10 to the 10 times fainter, 10 billion times fainter.
So that means we're going to need a 10 billion times bigger telescope to see these things.
It could well be there are some stars out there that are emit a lot more X-rays than the sun because they're hotter or have more flares. But 10 billion's a very big number to overcome. So at this point, it may have been that X-ray astronomy was over. However, some of the researchers in the field didn't give up. Nowadays, probably they would have got no more funding to keep on their research, but back then there were some people who thought, well, let's give it a go. We don't know until we see. And it occurred to them that there might be one other source, this one over here, the moon, that might emit measurable amounts of X-rays. I mean, how does the moon emit X-rays? The moon isn't that hot. Well, the idea was that the solar wind, these particles flung out at half the speed of light from the sun, protons, and mostly protons, will smash into the moon.
Yep.
And maybe when they smash into the moon, they will liberate X-rays.
So this is some version of the Large Hadron Collider, just the nature's version on the moon. So you could crash things in and you get flashes of light and other activity. And not a foolish way to go and create some interesting conditions to observe.
Yeah, and the calculations were very uncertain, but it looked like maybe if you built a better detector, certainly the one that picked up the sun wasn't going to be enough, but if you built one that was maybe 100 times better than that, then maybe we could pick up the moon.